Okay, get ready for this one. Buckle down. It's a lot of slides. It's a lot of information. This is your official introduction to orbital mechanics. I know we've covered this already, but just as a quick recap, orbits are a closed path around which a satellite or planet can travel. Johannes Kepler discovered that they weren't circles, but rather ellipses, and that this was something that he did with very little technology, no calculators, no computers. He just relied on his observations and working through the math by hand. He derived these laws and the equations related to them from just observations of how the satellites, and at the time they were all natural and not human-made, orbited the Earth. He came to the conclusion that it was done in an elliptical shape. Elliptical orbits remain fixed in space, and the Earth then spins under a fixed satellite that's orbiting it. Okay, so we also know that if we take a cone and we slice a section of that cone, we will get an elliptical shape. We do it at an angle, get an ellipse. There's a major and a minor axis, so therefore there's a semi-major and a semi-minor axis as well. It's a two-dimensional shape produced by a plane fully intersecting a cone. Plane intersecting the cone at an angle perpendicular to the cone's center will form a special ellipse that we call a circle. Now, this entire lesson, we've been asking very simple questions like, what is an orbit? What is a satellite? What is the moon? We're going to ask, what is an ellipse? We know this. A circle is a set of points fixed from a center point. In other words, they're a constant distance from a focus. They have a center point and a radius. Two of the radii going all the way through is like having a big axis, and that is what we refer to as the diameter. So in this image, A is a constant. This is an ellipse. Technically, both are an ellipse. A circle is a special kind of ellipse. Now, not all ellipses are circles, but all circles are technically considered ellipses. An ellipse has two foci instead of just a center. Sum of the distances from the foci is constant. In other words, if I pick any point out on the perimeter of this ellipse and I connect it back to both foci and I add those distances together, they will always equal the same value. Remember that a circle is an ellipse with both foci co-located. Satellites orbit Earth with one focus at the Earth's center. Other focus is an empty point which may or may not be within Earth's boundaries. This is why they're elliptical. One of these 2 points would be Earth, and the satellite would travel around it. So let's break this ellipse down just a little bit further. A, this A here, defines half the major axis. B, that's this B here, defines half the minor axis. The major axis is kind of like a diameter. It goes from one point on the ellipse through both foci and the center and out to the point opposite of it on the ellipse. It's the biggest axis. It's like the diameter, but it is a special circumstance of it. And perpendicular to it, the shortest points of the ellipse going through the center is the minor axis. A defines half of it, B defines half of the minor. The C that we see down here is half of the distance between the two foci. It's the distance from the center of the ellipse to either one of the two foci. So if we know the distance between the two foci, we can find where the center is by taking its midpoint. For a circle, A and B are equal to the radius. And both focal points are co-located at the center of the ellipse. In an ellipse, we have two radiuses. We have from one foci to a point on the ellipse, and then from that point back to the second foci. We're going to start talking about how diverse orbits can be. In the past, we talked about the fact that we have these basic orbits, things like LEOs, MEOs, HEOs, polar, Molnias, GEOs. All of these are just the basic definition of these orbits. Now we're going to get into something a little more, well, in depth. Let's describe the orbits. We can do this using a set of parameters that we call orbital elements, also known as Keplerian elements. There are 6 parameters to these. That's all of our Keplerian elements that we see here, 2 of them that'll describe the size and shape of an orbit, 3 of them that'll describe the orientation of the orbit in space, and 1 that describes the location of a satellite within the orbit, plus a timestamp. Now, 2 describe size and shape. 3 describe the orientation, where it is in space. And then another one will describe where the satellite is on that orbital path. 2 for size and shape. 3 to tell us where it is, and 1 that tells us where the satellite is on the path. Eccentricity describes how round the orbit is. It describes the shape of the ellipse in terms of how wide this thing is. We represent this as a lowercase e. Whereas a circle has only one diameter, an ellipse has many, all with different sizes. The largest diameter is called the major axis. The smallest diameter is called the minor axis. Instead of radii, we call half of these axes the semi-major axis and the semi-minor axis. A circle has only one major and minor axis called the diameter. Therefore, in a circle, A is equal to B. Therefore, B squared over A squared would be equal to 1. Therefore, in this formula, we would solve for the square root of 1 minus 1, or the square root of 0, which is 0. So the eccentricity of a circular orbit, as described by this equation of the square root of 1 minus b squared over a squared, is 0. Circular orbit, eccentricity of 0. We are describing its shape. Eccentricity can vary from 0 all the way up to 1. Eccentricity has that value of somewhere between 0 and 1 for only closed orbits. But once the eccentricity equals 1, we're getting into what's referred to as open orbits. Open orbits can be parabolic, an eccentricity of 1, or hyperbolic, an eccentricity that's greater than 1. But remember, an eccentricity that's equal to 0 means circular. An eccentricity of 1 or greater means the orbit is not closed. We would use these for interplanetary missions. Satellites in these same type of orbits don't come back to their starting point. So their orbit is open. All right, in this slide, we're looking at some examples of orbits that only have their eccentricity changed. Everything else about them is the same. The eccentricity of the green one is getting closer and closer to that one value, 0.74. The eccentricity of the purpley pink one is 0.6. The eccentricity of the orange one is 0.4. And the eccentricity of the red one is circular. It's 0. Notice how the eccentricity value helps us describe how elliptical this orbit can be, or any orbit can be. Remember, we're talking about how wide that orbit is. So we're talking about how squished the orbit is, how elliptical it is. Now, obviously, this is only one of 2 Keplerian elements that describe size and shape. Orbits can have the same eccentricity but be different sizes. There must be a Keplerian element which describes how big the orbit is. So eccentricity is describing for us what the shape of our elliptical orbit is. Now, as we move on, I want to be clear. We said earlier, orbits are always elliptical, and that is true. We can have circular orbits, but remember, a circle is an ellipse. But an ellipse isn't necessarily a circle. So all orbits are elliptical. We can force satellites to maintain a circular orbit. Naturally occurring ones tend to maintain or do maintain elliptical, and they vary in their size and shape. Eccentricity, all about that shape. Semi-major axis is all about the size. It describes the size of the ellipse. It is half of the largest diameter. The major axis is what we're talking about. The semi-major axis originates from the center of the orbit, but we are located on Earth. This makes the semi-major axis difficult for us to visualize from our reference point. Okay, so a quick recap here. An ellipse has multiple diameters and/or radii, all of different lengths. The largest diameter is called the major axis. In orbital mechanics, it is the radius rather than the diameter that's used. Since this is half of the major axis, we refer to it as the semi-major axis. Okay, let's now point out some important spots on the orbit. I'm not always a huge fan of reading off of a slide, but I do want to read a little bit off of this slide for you here. Apogee, the point in an orbit that is farthest from the Earth. Perigee is the opposite of this, the point in an orbit that is closest to the Earth. Apogee altitude is the distance between the surface of the Earth and the apogee. Perigee altitude is the distance between the Earth and the perigee. Since we are located on the Earth, using altitudes rather than semi-major axes can make it easier for us to visualize the actual size of the orbit. While apogee and perigee are actually reserved for the use with objects in Earth's orbit, people often refer to the apogee and/or perigee of the Earth's orbit around the Sun. Technically, this is incorrect. In this case, the generic terms of apoapsis and periapsis should be used. That's A-P-O-A-P-S-I-S, apoapsis, and periapsis, P-E-R-I-A-P-S-I-S, periapsis, apoapsis. We could also use the terms that are specific for a sun-centered orbit. This is apohelion and perihelion. Apohelion, A-P-O-H-E-L-I-O-N. Apohelion, apohelion. And perihelion, P-E-R-I-H-E-L-I-O-N. Perihelion, perihelion. quick recap. Eccentricity, 0 all the way up to, but not quite including 1, because then we get into something that leaves a closed orbit and gets into open orbit. Eccentricity describes for us the shape of our elliptical orbit. 0 is circular, approaching 1 becomes highly elliptical. You get to 1 and beyond, and you're getting into parabolic and hyperbolic, where you have an open or non-closed orbit. You move past that and you get into what describes, as a Keplerian element, the size of our ellipsis or of our orbit. And with that, we're looking at the semi-major axis, or half of the entire distance from the apogee all the way to the perigee of the orbit. Half of it. But it's hard for us to get our mind around where that center point is that we're measuring half that distance, because it's not on Earth. Earth is one of the foci. The other focal point is somewhere out in space, and the center is the distance between those two, which is also somewhere out in space. Apogee and perigee define for us how far the Earth is from the furthest point away, apogee. That's the apogee altitude, is that distance, and perigee defines for us the point at which it's closest to the Earth, and the perigee altitude is that distance. I want you to pause the video and go Google search for typical space shuttle orbit or typical space station orbit. See if you can find out information about it and come back. Don't take long. I wonder if you guessed the typical altitude for such an orbit before you searched. Did you know that the radius of the Earth is 6,378 kilometers, or around 3,963 miles? The radius of the Earth. That's pretty big. A large altitude, like you see here in the slide, is often used for depicting orbits simply to make the illustrations readable. However, a typical space shuttle orbit is roughly 300 to 350 kilometers above the Earth. If a drawing of such an orbit were to be made to scale, the circle representing the orbit would be barely larger than the image representing the Earth, and we'd have no place to put our arrows and the words apogee altitude and perigee altitude. Speaking of which, for a circular orbit, the apogee altitude and perigee altitude are the same. They're equal to each other. Perfectly circular orbits has neither an apogee nor a perigee. It is undefined. Perfectly orbits can't really be achieved. Generally, circular orbits are described by their altitude, and semi-major axis rarely used in describing a circular orbit. Again, circular orbits can be forced to happen, but they are not something that we can really achieve. There is always one point at which the object physically has to be further away and closer. Let's take it further. We know eccentricity and semi-major axis are the first two elements. Eccentricity tells us about the shape, and semi-major tells us about the size. Semi-major axis is the only orbital parameter that can determine the orbital period. Now, this is a lot of information up here. Let's step through it. Time, or the orbital period, t, is equal to 2 pi times the semi-major axis, remember that lowercase a, raised to a power of 3 over 2. The gravitational parameter is what we put in the bottom. It's a mu. So 2 pi times a raised to the 3/2 power over the square root of my gravitational parameter. Gravitational parameter is defined by the universal gravitational constant times the mass of the central body. G, capital G, times capital M, the mass of the central body. Not just mass and not just gravity, but the universal gravitational or gravitation constant. 6.6 times 10 to the negative 11, blah, blah, blah. You get it. It's there on the screen. So what we're saying is that a period of time deals with 2 times pi times the distance of our semi-major axis raised to the 3.5 power over the square root of the gravitational parameter, mu. All of this simply means that Kepler's third law is the square of the period of a planet, and it is proportional to the cube of its mean distance from the sun. Let me say this again. This can all be translated as Kepler's third law. Square of the period of a planet is proportional to the cube of its mean distance from the sun. If you rearrange this equation, you'll find that. Let's take a look at the next slide. Here we see that the only thing that would change about these circular orbits, these elliptical, special elliptical orbits here, is the A. The only variable in the equation is A. Mu and Gm are constants. Pi is a known, it's a constant. 2 and 3/2, knowns. It is the 3/2 power that we're concerned with here. The larger the A is, the larger this term is. Therefore, the larger A, the greater the period. And that makes sense. The bigger the diameter, or the bigger the radius, the bigger the major axis, or in this case A, the semi-major axis, the longer that distance, the greater that distance, the longer this value, or the bigger this value is going to be, and the longer the orbital period will become. Okay, let me pose a question to you. What is the approximate orbital period of the International Space Station? It's roughly 90 minutes. Think back to what we talked about with the kind of orbit that the space station has to be in. All right, that space station is in a very, very close orbital, or not orbital period. It's in a very, very short or small semi-major axis, a very close orbit. Obviously, as we get further out, there's more distance to cover, and so the orbital period for something with a bigger A is going to be greater. Still on with the semi-major axis. And I want to remind you, we talked about very simple basic orbits before. We're going to look at how diverse they can be. You might argue that these orbits are not the same, but they really kind of are. Their eccentricities vary so widely, their appearance of size can be a bit distorted. All right, the only thing about these orbits that is different is their orientation around the Earth and the eccentricities, but their size is the same. They have the same semi-major axis. They just simply are located in a different orbital plane, or the relation of where they are to the Earth is slightly different. Eccentricity can throw off how the size of these might look, but these all have the same semi-major axis. Okay, with that said, orbits may have identical sizes and shapes. In other words, they may have the same semi-major axis, same A, and the same eccentricity, same E. Yet, they can vary in their orientation in space. 3 Keplerian elements define this orientation. 2 define size and shape. 3 define the orientation. The first one is inclination. The second one is what's referred to as the right ascension of the ascending node. And the third one is referred to as the argument of perigee. What we're saying is that size and shape are described by these physical things of how big and how squished our elliptical orbit is, right? Size, shape, semi-major eccentricity of the orbit. But we also have to think about how much that orbit is tilted, or the inclination of it, and then we have to get into what right ascension of the ascending node, abbreviated as RAAN, and what the argument is of the perigee. So here is inclination. It's measured in degrees. It's fairly easy for us to think about. It's the angle between the Earth's equatorial plane and the plane of the orbit. It describes the tilt. So if we draw straight out from the equator a ring, that is our equatorial plane. How much this orbit goes up or down from that equatorial plane is its inclination. The one that we see that's yellow is the smallest, 5 degrees. Then red is 25. Then I is 45 degrees. Pink is 45 degrees. Then orange is 75 degrees. Almost a polar orbit. You gotta love the weird little things that go into these slideshows. So yes, in talking about the inclination, it's important for us to talk about the ground trace. I'm going to read again off of the slide. We have a satellite. It's in orbit. And if a long string with a marker is tied to the end of it, and it hung down to the Earth, the path that marker would trace over the ground is called the ground trace. It's a projection of the satellite's orbit onto a flat, two-dimensional Earth. The satellite appears to move westward on most conventional orbits because the Earth is rotating eastward. More on that later. Okay, we're going to take and go from three-dimensional concepts or pictures of orbits to what this looks like is two-dimensional. That projection that we're going to look at is called the ground trace. A fair amount of information about the satellite's orbit can be obtained simply from that ground trace. This is a ground trace. After a full day, the ground trace of a satellite with an approximate 90-minute orbital period would look like this. The Earth is continually rotating below the orbit of the satellite. The ground trace eventually spans all longitudes. Here's 0 or the equator. And we see our satellite is traveling along a path that it would reach a particular height, measured in degrees, that we think of as being the highest point of its inclination. In other words, it is the highest point up in its inclination. This is the measure that we see of it as it has left that equatorial plane and reached all the way up to here. So somewhere between the 30 and 60 degrees. And then down here the same thing, probably close to something like 45. So if we have a satellite with an inclination of around 45 degrees, then it's going to create a ground trace that looks similar to this. Remember, every 90 minutes, it goes from its starting point to the same equatorial plane starting point. Now let's follow this through with my mouse. I move through here and I travel along this path until it starts to arc back down. I'm not going to be able to see these far northern countries because my equator or my inclination doesn't go high enough for that. It comes back down, passes through India, goes on past Indonesia and into Australia, doesn't quite get all the way down into the far south part of our southern hemisphere down here with Antarctica. But as it does come back down through here past Australia, and it picks back up over here on this side. And then you'll notice that when it swings back up and it gets to where the equator is again, it hasn't gotten back to where it was when it started. It's moved back. And it continues to do that as it loops around again. Notice now it's not going through India, but rather Saudi Arabia. Now it passes through the Indian Ocean and now to this side of Australia and back around again. And it starts to kick back up a little quicker, and now it's even further out over the Pacific. So as it's orbiting around, the Earth rotates underneath it. Let's go back to inclination now and continue to think about it. Inclination determines the northern and southern latitude limits over which the satellite orbits. So when we look at that ground trace, the highest point of that ground trace and the lowest point of that ground trace tell us what the inclination is. So that example of a satellite with a 45-degree inclination will have a ground trace ranging from 45 north to 45 south. You can determine this by simply looking at its ground trace. And here's a ground trace of a whole bunch of other orbits. They have varying inclinations, and they orbit with a slightly different period. The inclination of the satellite in degrees is equal to the northern and southern limits of the ground trace in degrees of latitude. A satellite wishing to obtain imagery of an oil spill near Alaska should have an inclination close to the latitude of the oil spill. The inclination of an orbit can be obtained by just looking at the ground trace. Do these inclinations that you're looking at seem to correspond to the degrees of tilt relative to the equatorial plane which you see in the 3D picture up above? They're the same colors. Notice that the yellow one has a very small, about 5 degrees or so, of inclination. So it won't go very far from the equator. Whereas the orange one is nearing a polar orbit and does reach much, much higher, closer to 75 degrees north and 75 degrees south. An orbit with an inclination of 0 degrees is called an equatorial orbit, and an orbit with an inclination of 90 degrees is therefore called a polar orbit because it goes over the poles. A satellite in an equatorial orbit will pass directly over the equator and have a ground trace that looks like the image in the top. And a satellite in a polar orbit will pass over the entire Earth and have a ground trace like the one on the bottom. Based on what we've already learned about orbital parameters, we can determine that inclination and orbital period can be found from a ground trace. Inclination is noting the northern and southern latitude limits, and orbital period can be determined using a simple calculation. Since inclination has been discussed in detail on the previous slides, the orbital period of a satellite is something that we're going to talk about next, and how we can get it from a ground trace. So in the next slide, I'm going to walk you through the process of computing that inclination. But to prepare for this, I want you to note the longitudes of the first and second passes of the satellite in this ground trace. The most common reference points used for such a calculation is the point where the satellite crosses the equator, or 0 degrees latitude. In the example we're going to see, this occurs at 0 degrees longitude for the satellite's first pass and 25 degrees west longitude for the second equatorial crossing. Ready to use this information on the next slide? Let's determine a satellite's orbital period from that ground trace. Step 1. Recall that the orbit of a satellite remains fixed in space, and the Earth will move underneath it in a rotation. The westward regression of the ground trace, so how it moves as it goes through that ground trace to the left, or westward, is due to the rotation of the Earth. We need to determine how many minutes it takes for the Earth to rotate 1 degree. So in step 3, we have 1440 minutes, 1,440 minutes divided by 360 degrees. Step 3 refers to 1,440 minutes, which represents 24 hours times 60 minutes. Okay, that's where we get that value from. The Earth spins completely on its axis in 1 day, and this exercise assumes a perfect 24 hours for that day. In actuality, the Earth completes a rotation on its axis in a little less than that, 23 hours and 56 minutes. But for this lesson, we're going to simplify it to 24 hours. So step 3 shows 1,440 minutes calculated by saying 24 hours by 60 minutes. And we divide that by 360 degrees. This is 4 minutes for every 1 degree. Step 4 now has us determine how many degrees per pass the satellite's orbit regresses or moves westward on each consecutive orbit. Equatorial crossings being that common reference point that we'll use. If we use 25 degrees as an example, then we need to figure out how long did it take the Earth to rotate this many degrees. That's the period of the satellite. So 25 degrees times our conversion factor of 4 minutes per degree is 100 minutes. So if we use a 25 degree and we know that it takes 4 minutes per degree, then it's going to take 100 minutes. All right. So we can determine a period for a satellite by looking at what its ground trace shows us for that inclination and seeing how far it moves as we go from one spot as it crosses the equator to the next spot that it crosses the equator. If we know that the satellite regressed 25 degrees, then we can determine that it took 100 minutes for that satellite to make it around the Earth one time, and in that amount of time, the Earth rotated by 25 degrees. Since we can go 4 minutes per degree, we get 100 minutes. Now, I'm not going to lie. Right ascension of the ascending node is probably the most difficult orbital parameter for students to grasp. That doesn't mean that you can't. It is a little challenging, though, at first. If you think about a hula hoop and a basketball. Basketball is the Earth, hula hoop is the orbit. I can place that hula hoop around in any kind of inclination with the basketball. I can push it further, or I can change the shape slightly of the hula hoop. But how I twist the hula hoop so that it can tip itself, this is the right ascension of the ascending node. Right ascension of the ascending node can be tricky, but it can be easily explained. And honestly, it can be explained in a single word: twist. So each of these satellites have identical eccentricities, so their shape, and they have identical semi-major axes, so their size, and they have identical inclinations. So we're talking about the tilt that they have from the equatorial plane. Yet they may still be oriented differently in space. They can be rotated or twisted about the Earth in various ways. Each satellite here starts out above a different longitude on Earth. However, longitude can't be used as a reference point because it moves. The Earth rotates, and it does so underneath the orbit, changing the reference longitude on each satellite pass. And we saw that earlier by having a regression of 25 degrees for that exampled orbit. So, right ascension of the ascending node is what we need. We need some type of fixed point in space to do this with. Let's break RAN, or R-A-A-N, right ascension of the ascending node, up into two parts: right ascension and ascending node. Ascending node comes first. This is the point on the orbit where the satellite crosses the equatorial plane in an ascending direction, going up. That is, traveling from the southern hemisphere into the northern hemisphere. 180 degrees of the ascending node, the satellite has a descending node. And a node is just a point, right? So where it's crossing the equatorial plane, because it's this elliptical orbit, 180 degrees over, is where it's crossing the equatorial plane again. It is this ascending node, this rising of it, which must be located using a non-moving reference point. And since the Earth is spinning underneath it, you can't use the Earth as a non-moving point for that satellite in orbit. This reference point is referred to as the right ascension portion of RAAN. Since we can't use an Earth-based reference point, we use a celestial reference point known as the vernal equinox. That's V-E-R-N-A-L. Equinox. E-Q-U-I-N-O-X. Vernal. V-E-R-N-A-L. Equinox. E-Q-U-I-N-O-X. Vernal equinox. This point, this celestial reference point, or the first point of Aries, is what we'll use. The angular measurement of the right ascension, is 0 at the vernal equinox. If the ascending node of the orbit is aligned with the vernal equinox, the RAN is 0. Let's back that up. The reference point is the right ascension portion of the ascending node. We can't use an Earth-based one, so we pick a point out in space. It's known as the vernal equinox, or the first point of Aries, A-R-I-E-S. The angular measurement of the right ascension is 0 when it's on the vernal equinox. If the ascending node of the orbit is aligned with the vernal equinox, then we have a right ascension of ascending node as 0. RAN refers to the vernal equinox, which is determined by the orientations of the Earth's rotation axis and the orbit about the Sun, or around the Sun. These orientations vary over time. In actuality, our, quote, fixed celestial reference point is not really fixed. Therefore, several different coordinate systems may be used which, quote, point to the place in space where the vernal equinox was at a given date. For example, the B1950 coordinate system points toward the location where the vernal equinox was at the onset of the year 1950, and the J2000 to the point where it was at the onset of the year 2000. By now, you're probably scratching your head and saying, what? Yeah, no wonder this is difficult. Bear with me. Okay? It is all about the twist of the orbit and being able to look at a point that we say is fixed in space, and that we can then argue how much that angle difference is of when we are looking at this satellite in orbit going up from the equatorial plane to where that point is in space. How much we have twisted our orbit. Eccentricity, semi-major axis, shape, size, inclination, how much it's tipped up from the equatorial plane, right ascension of the ascending node, the twist that our orbit has when we are comparing it to what we consider a fixed point in space, and where that satellite in orbit is as it comes up out of the southern hemisphere. All right, this leaves us with the argument of perigee. So these orbits all have the same E, A, I, and omega. They all have the same eccentricity, semi-major axis, inclination, and the same right ascension of ascending node. What is different about them is that they have still yet another way of describing the orientation, and this is the location of their perigee point. And it can vary based on the orbital plane. Argument of perigee describes the orientation of the orbit within the orbital plane. Where is the apogee and where is the perigee? It's measured again as an angle from the ascending node to the perigee point in the direction of the satellite's motion. So remember, the ascending node is how it's coming up from that southern hemisphere. and we're going to compare where that is to where the perigee of our orbit is. And we do this in the direction of the satellite's motion. This is referred to as argument of perigee, and as the name implies, the argument of perigee is only mathematically defined if a perigee point exists in the orbit. Up to this point in the lesson, circular orbits have been used heavily for examples, but a circular orbit has no perigee. Therefore, on this slide, highly elliptical orbits are used so that the perigee point becomes obvious. The orbits in this slide are identical in all parameters except for that argument of perigee. All of them have an ascending node. All of them have the same ascending node. All of them have the same tilt or inclination. The red and orange orbits are the easiest for us to kind of observe here because they're opposite of each other, and the yellow and blue might be as well. With the orange orbit, the ascending node occurs at perigee. Hence the argument that perigee is 0 degrees. However, the red satellite experiences its ascending node at apogee, or 180 degrees from perigee. While argument of perigee is undefined in circular orbits, a true perfect circular orbit is not possible in reality. So while seemingly circular, most, quote, circular orbits do have some apogee or perigee, albeit very, very close in distance. All right. Argument of perigee based on right ascension of ascending node, which is based on a vernal equinox, a spot that we pick in space that we say for at least a while is the same. We have to keep pointing to where it should be. And we can look at how that satellite is relative to not only that spot, but its perigee to that right ascension of ascending node, to that ascending node. We can look at how the orbit is tilted from our equatorial plane. We can look at how big the orbit is, and we can look at how the orbit is shaped. Is it highly elliptical, or is it closer to being circular? This leaves us with the very final element, the sixth one, true anomaly. After an orbit and its orientation have been thoroughly described in these 5 ways, there must be a way to describe the satellite's position within an orbit at any instant. It's very important to note that a timestamp must always be associated with true anomaly. For example, if a time is not provided to state when a satellite is at a perigee point, it would be impossible to know when it will be at its apogee point or any other point along the orbit. Therefore, when a complete Keplerian element set is provided, eccentricity, semi-major axis, inclination, the right ascension of the ascending node, the argument of perigee, and now also true anomaly, time must be included to make this element set meaningful. This time is referred to as the epoch. True anomaly is an ever-changing parameter, which makes sense. The satellite is always moving. If multiple satellites occupied the same exact orbit, but both had different true anomalies, they would orbit over different locations of the Earth at any given moment. It's the angle between the perigee point and the satellite's location, measured in direction of the satellite's motion. This value is constantly changing as the satellite moves. True anomaly is 0 degrees when the satellite's at perigee, 180 degrees when the satellite is at apogee. Notice how these all start to build on each other. The Keplerian elements consist of 6 parameters, 2 that describe size and shape, eccentricity, semi-major axis, 3 that describe the orientation of the orbit in space, inclination, right ascension of the ascending node, and the argument of perigee. And then you have 1 that describes the location of the satellite with the orbit, true anomaly. But we also have to take a timestamp of it, referred to as an epoch. Must be included every single time we provide a Keplerian element set. This is so that it is known when this set of values was accurate for the satellite or when the snapshot of the orbit was taken. Kepler also came up with some planetary motion laws. His first law states this: satellites will travel around Earth in elliptical paths with the center of the Earth at one foci. We've seen this. Step or law 2 is that a line drawn between Earth and a satellite will sweep out equal areas during equal time periods anywhere along the orbit. So his second law hasn't really been discussed up to this point, but you have seen the results of it. When viewing highly elliptical orbits, you might notice that the satellites travel fastest at perigee and slowest at apogee. So in other words, as we get to that point that's furthest away, they are going the slowest they will in their orbit. And as we get to that point that is closest, perigee, we're talking about the fact that these things are whipping around very quick. Gravity of the Earth is pulling them back in, speeding them up as they go from out here at their apogee to here at their perigee. So they're traveling much faster. This area that's swept out over a period of time is the same as this area that's swept out over a period of time. The time is the same amount. The area is the same amount. The distance they are away from the Earth is what's different here. These areas have to be equal. First law says they're going to move in elliptical paths, with the Earth being one of the foci. The second law says that the area they sweep out are equal. No matter where they are, if we use the same amount of time, the path that it sweeps, that area is the same. This means the speed of a satellite can change as the distance between it and the Earth changes. At perigee, the satellite is going the fastest. At apogee, the satellite is going the slowest. And this brings us back to that time equation that we saw earlier, that period of time. And this is Kepler's third law. Remember, we said if we can rearrange this, we'd get it. The period of an orbit, t, is related to how far it is the semi-major axis. All right, so how big it is, the size of my ellipse. T squared is equal to 4 times pi squared over mu times a cubed. The only thing that changes here, the only variable when we're solving for the t, is a. So there are 3 laws. Kepler set. The Keplerian element set shown or chosen for any given satellite is highly dependent on its mission. Certain orbits are better suited for certain missions. LEO must be related somehow, right, to the constellation Leo or the lion. Well, no, there's no connection there. Remember, we're talking about low Earth orbits. We've discussed these. No specified minimum altitude, really close to the Earth, short orbital periods. The limited swath area that they have to when they view the Earth's surface. And pretty much everything we've done since we stopped going to the moon has been in an LEO. But why is weather and imagery what we think of when we're thinking of these Earth-observing satellites or orbits? If we consider the fact that it's so close to the Earth, we can get a very, very high resolution imagery of it, and we're going to see maybe the same kind of place along the Earth over and over again. Okay? These LEO orbits are great because we can get real high resolution of them at these close distances. Remember this, geostationary. It stays over the same location. We achieve this by getting to an altitude of around 36,000 kilometers or 22,000 miles. Our inclination is exactly 0 degrees. They only exist over the equator. They can only see around 70 degrees north and south of the equator. And they are mainly used for communications or permanent relay stations in space. Only one altitude has that period of 24 hours. All geostationary orbits are in that ring, and that ring is called the geostationary belt, and it is really getting full, packed, dense. Okay? When a geobird dies, when a satellite dies, it's got to be removed from the slot in the geobelt because it's got to make room for another satellite. We usually, towards the end of its functional life, boost it into a higher orbit. But that leaves it as space junk. It's difficult to orbit exactly in a 24-hour period at 0 inclination. They typically have a slight inclination to them, and this is why if you look at a true picture of it, you're going to see that this band isn't a single line, but rather a little bit thick. Satellites drift slightly north or south of that equator and slightly east or west due to imperfect periods. Small orbit adjustment burns can be performed, and they're called station keepers. Satellites with that 24-hour period and non-zero inclination are geosynchronous. And geostationary and geosynchronous are often interchanged. I want to point out the scale on this figure. The inclination and orbital drift may look significant, but the inclination is still less than 1/4 of a degree. and the satellite drift less than a full degree of longitude in a week's time. Still, over time, such adjustments become too great and must be corrected. This is what the real geobelt looks like. Here we have taken ground traces and projected them out to a geostationary altitude. Ground traces of all operational geostationary satellites are shown here in that geostationary altitude, and large inclinations create this figure 8 type orbit ran out of station keeping fuel. Sine wave orbits are being drifted to new locations, and orbit color corresponds to the participation in specific data sharing programs, not orbit related data. So this slide might be a little difficult for you to interpret. It is important that you understand they are not really orbits that you're seeing here. An orbit, as you've already learned, is a closed path, circular in the case of geostationary satellites, or close to. This slide is showing the ground traces that are projected out into space, whereas the ground traces are normally shown against a 2D map on Earth or of Earth. However, this representation allows for easy visualization of the, quote, true geostationary satellites versus those with significant inclinations. A satellite may be fully functional long after it's run out of station keeping fuel. In that case, it would not be financially prudent to discontinue use of the satellite. Instead, the satellite is still used although it begins to acquire an inclination that does increase over time. And depending on the location of the ground station and the inclination of the satellite, continuous 24-hour contact with the satellite may still become impossible. Remember before when we talked about a molly? And we talked about how it had this different kind of orbit from everything else so that it could see Russia for a long period of time? Well, think about it now. Highly inclined and highly elliptical. That high inclination allows it to cover over Russia. That high eccentricity gives a large apogee altitude and a very slow velocity at apogee. If apogee is over Russia, then the satellite hangs over Russia. Kepler's second law. Here's the example of it again. Remember, it's going to be going slowest as it reaches that furthest point away. Once it goes past that point, it does start to pick up speed again, but it whips around so quick that it slows as it climbs. Remember that Molniya ground trace and how it looked. Think back now to polar orbits. Because that inclination of the orbit is 90 degrees, it's constantly over the orbit and will eventually pass every part of the Earth. A special type of polar orbit called a sun-synchronous orbit passes over the same part of Earth at roughly the same local time every day. Think about why that might be useful. What if we're measuring air quality or the temperature of a certain area? The variations in those values, which would naturally occur due to the time of the day, can be eliminated with a sun-synchronous orbit. Think about constellations. A single satellite isn't as useful as having multiple ones that do the same thing that coordinate with it. GPS systems, Starlink. Think about the complexity of these orbits, their inclinations, their right ascensions of ascending node, their argument of perigee. All of those things are very important to describe where its orientation is, and then knowing what its true anomaly is, where it's located in that orbit. They're probably all going to have roughly the same eccentricity and the same semi-major axis, but their orientations need to be different. Their true anomalies need to be different. You may have multiple ones that are in the same orbit but spaced out by certain periods of time. Come back to these questions now and think about them. If Norway wanted to obtain a satellite imagery of all of its major urban areas, what type of orbit would be appropriate? And could researchers down in Antarctica use a geostationary satellite for communications? Well, for the Norwegian satellites, that satellite should have a high inclination, since Norway is pretty far in the northern latitude, and a low altitude circular orbit. The inclination is approximately 70 to 80 degrees with an altitude of several hundred kilometers. What about the people in Antarctica? Well, no, they can't use a geostationary satellite for communications because the latitude of Antarctica is too far south. However, options do exist. So what are those options? Well, option 1, old geostationary satellites that have acquired significant inclination, we're talking about greater than 10 degrees here, can provide continuous communications for around 6 hours a day when they're in the southern portion of their figure 8 ground trace. And option 2 is that researchers in Antarctica can also communicate using low Earth orbiting communication constellations such as the Iridium satellites. Now, if you bared with me through all of that, I highly appreciate it. That was an hour and almost 15 minutes. There was a lot in there. Remember, 2 Keplerian elements, size and shape, semi-major axis and eccentricity. 3 that describe its orientation. How it's tilted, how it's twisted, right? And then also the relative turn of the orbit, how it is compared to that ascending node and the perigee of the orbit. And then we have to look at the true anomaly. We have to look at where the satellite is in its orbit with a timestamp so that we know when it is in that orbit. And then from those things, from those 6 Keplerian elements, we have his 3 laws, right? Keplerian's 3 laws. And they're not all that complex, but it's probably a good idea to review them. If we're talking about his first law, then what we're really getting into is more of a concept of what he just came up with. The fact that he figured out satellites travel around an Earth in an elliptical path, and Earth is one of the 2 foci. And then his second one said that as these orbits happen, and we look at the same time period, the path that it sweeps out, the area of it, is the same no matter what part of the elliptical orbit we look at, as long as the time is the same. There is a quality to them, a balance to them, a harmony to them. And his third law describes that period orbit, in which it says that the time squared, the period of the orbit squared, is equal to 4 times pi squared over mu times a cubed.